Indeed, I'll be talking about some work that I was doing while a postdoc in Max Planck Institute for Software Systems. And this is joint work with a lot of different people from 3 different institutes. The first listed co-authors are from the Technische Universität Dresden. Then the rest are from the Max Planck Institute for Software Systems, except for James Worrell, who's from Oxford University. So yeah, indeed, currently I'm in Liège, but this is work done while I was at the MPI. So let me just first start by some motivation. Why on earth do you study linear dynamical systems in a software systems institute? Well, you want to, in software verification, you generally just want to know, does a program work correctly? And what you do is you start modeling the program, and you have these kinds of distinct blocks that you can usually decompose your program into. You start modeling these blocks separately, and the correctness of each of the blocks ensures correctness of the whole program. So one question you might ask is, does this while loop terminate or halt? And that's pretty important in verifying programs. So if we consider a loop just over the integers with 3 variables here, you have a first initialization of the variables. You then go into this while loop here, and you do some updates. Well, here these are linear updates of the variables, and yeah, that's good. So we would start modeling this as a dynamical system. So first of all, you have your initial point x0, 1, 2, 3, and you have an update matrix. Essentially, well, it's a linear update, so you just map the previous state with this matrix. And now inspecting this this while loop, you see that your loop will halt if and only if there exists an n such that the nth power of your update matrix applied to your initial point equals this target point 210. Geometrically, well, this is, I mean, you already saw it is a dynamical system, and geometrically, you have your starting point in ambient dimension D. You have a linear update map M, and you define an orbit of this point. So then, if we consider the previous example algorithm, the loop halts when you hit the specific point, and this is actually an instance of a problem called the orbit problem. Does the orbit contain the target point? And well, if you just look at this example, it's pretty easy to see that you won't hit this point. And in general, this is a decidable problem when everything is over the rationals, or even more algebraic, if your entities have algebraic entries. So this was an instance of a kind of a reachability problem in linear dynamical systems. You start from a point and you want to know if you ever end up hitting another point or hitting other sets. And well, here we already bump into problems, open problems, that is. So Scolums problem, you can formulate it as a reachability of a hyperplane. So you just have your initial point X, you have a update matrix M, and then, well, you want to know if you hit this hyperplane defined by U. This is an open problem since the 30s. Well, I mean, if you allow these kinds of algorithmic problems to be already stated in the 30s in a meaningful way. It is decidable for instances with dimension at most 4. So in loop terms, you'd have at most 4 variables. And it's decidable if you have real algebraic entries, not just rationals. But it's already open for systems with dimension at least 5. And well, Scolums' problem, usually it's a problem on linear recurrence sequences. You want to know if a linear recurrence sequence hits a 0 or not. It is a frustrating open problem. So there are prominent researchers are describing the situation like so. For example, Richard Lipton says that it's a mathematical embarrassment, and Terence Tao says it is faintly outrageous that this problem is still open. It is saying that we do not know how to decide the halting problem even for linear automata. And you can see where this linear automata business comes from. Okay, so in general, you have your initial point X, you have your update matrix M, and now you have a target set T. And you want to decide if the orbit ever is contained in this target set T. For linear loops, T encodes the halting condition of the loop, if you're modeling linear loops. And well, reasonable targets would be semi-algebraic targets. So they are sets that you can define using Boolean combination of polynomial equalities and inequalities. I mean, you are talking about loops on or programs on computers, so that's a reasonable assumption. But already the Scolum problem falls within this regime. It is indeed, it's this hyperplane reachability, and well, it's plain to see that this is a semi-algebraic set, this hyperplane. Similarly, you can have the positivity problem. Again, it's whether you reach a half space defined by a particular vector. And this, you can state it as a positivity problem, which is a provably mathematically hard problem. So what do I mean by that? It means that if you can decide the positivity problem, this would entail major breakthroughs in the field of Diophantine approximation, so an old field in number theory. Well, it's not expected to be an easy problem. Okay, so what can we do? Well, we have to restrict our target somehow. I mean, to have any hope to decide reachability, for example. So how do we do this? We're going to restrict the dimension of the targets. And this is not the linear dimension. I'm going to say it's intrinsic dimension, but it's really a notion of dimension for algebraic sets. So for example, in 3D ambient space, you can think of a surface. So here, either the blue surface defined by 2z cubed plus 2y equals x, or this orangey surface defined by x plus y cubed equals z. And these will have intrinsic dimension 2 because they're flat. That's the kind of the idea there. And now if you think of a curve, you're going to have intrinsic dimension 1. And for example, if you consider the intersection of these two surfaces, you get this curve in the black. And that, again, I mean, it's an algebraic set, and that will have intrinsic dimension 1. However, if you consider like the linear spans of the elements of these surfaces or curves, they're going to be 3-dimensional. So it's really about this intrinsic really means that it's nothing to do with the ambient dimension. Okay, so our targets, these are going to be examples of our targets. I'm going to state the theorem later on. But if you consider these semi-algebraic sets in dimension 4, you notice that T1 and T2 are contained in three-dimensional subspaces. And this is because of their first defining equations. You can see in T1, you have T plus U plus V minus W equals 0. It means that you're in a three-dimensional subspace. T3, on the other hand, has intrinsic dimension 1. This is not necessarily easy to see, but one of the ways is to show that each pair of the coordinates, if you project to those coordinates, they will satisfy a bivariate polynomial equality. That's anyway, it's still a curve-like object. Another example would be 2D polytopes in ambient dimension, arbitrary ambient dimension. And well, these are going to be sets contained in 3D subspaces. Again, this is pretty easy to see. Okay, so these are the sets we're interested in. So either you're contained in a three-dimensional subspace, or you have intrinsic dimension 1. And this is the theorem. The reachability problem is decidable when T is a semi-algebraic set of intrinsic dimension at most 1, or which is contained in a subspace of linear dimension 3. Right. So, okay, this is very restricted. On the other side, we show that it's actually quite difficult to get past these assumptions, because you get this kind of Scolum hardness if you have a two-dimensional, intrinsic dimensional semi-algebraic target. So it means that if you can solve this reachability problem for a 2D algebraic, semi-algebraic target, you can solve Scolum's problem for at dimension 5, for example. And to close the picture, there's a, well, it's not an old result, but it's a recent result saying that, again, you have hardness if you allow your objects to lie in subspaces of dimension more than 3. So if you want to have a 3D polytope, and you want to, your target is a 3D polytope in ambient dimension 4, then you'll get the Scolum. You'll have to solve the Scolum problem. And then this mathematically hard problem is the reachability of a 4D polytope in ambient space, ambient dimension 4. This mathematically hard means that, well, essentially it's this positivity hardness. So you'll be deciding the positivity problem. Okay, so what I'm going to discuss further in this talk is well, I'm going to give a proof sketch of this, the first theorem, mainly focusing on this one-dimensional semi-algebraic targets. Then I'll explain how you can actually generalize this reachability to deciding more maybe interesting properties of your system. And if I have time, I'll talk a bit about the hardness. I'll give a proof of the hardness indeed if I have time. But first, let's go to this first proposition. Again, you have your initial point X, you have your update matrix M, and your semi-algebraic target of intrinsic dimension 1. I'm saying that this is decidable, whether your orbit enters this semi-algebraic set. And well, how do we do it? We show that there is a computable upper bound on the first instance when you hit your target. That's essentially what this is saying. And yeah, then it's clearly decidable because you can just try everything up to this computable n, and that's it. Well, how do we do this? Well, first of all, we transform the system into Jordan normal form. I mean, this is classical first or second course in linear algebra. And this allows us to focus on invariant subspaces of our matrix. And we get a fairly decent case analysis depending on the spectrum of the matrix. So in most cases, we're actually solving instances of the Scolum problem. But there are corner cases where you can actually model the system or hitting the target using codings of rotations. And that's the interesting part. Because, well, I'll go into that later on. But well, okay, here, first of all, we're transforming into Jordan normal form. This is means that you have some invertible matrix S and a Jordan matrix J. It's a block diagonal matrix with Jordan blocks on its diagonal. And these Jordan blocks have a particular form. They have the eigenvalues on the diagonal, and then on the super diagonal you just have ones. Everywhere else you have 0. So of course, yeah, taking powers of M means that essentially you're taking powers of J, but you're doing this similarity transformation. So if we're looking for M to the n of X to reach the target, essentially you're looking at J to the n applied to some other related vector, whether that hits a related target. Okay, but then the equations look like this. So, I mean, your points of the orbit. And well, okay, as I said, it's going to be a huge case analysis. I'll just explain where the Scolum problem comes from. When you look at the lowermost equations that you get from this transformation, is if you have two multiplicatively independent eigenvalues, meaning that no integer power product of them equals 1, except for the trivial case, then yeah, this is when we get the Scolum's problem. So now we're just going to focus on these, like these the last coordinate of each of these blocks that we get. So now, using the fact that T-prime, well, it's just a linear transformation of a dimension 1 semi-algebraic set, you're going to get a dimension 1 semi-algebraic set. This means that there exists a bivariate polynomial such that whenever you're in your target set T prime, this implies that your polynomial vanishes. Okay. But now if you look at this polynomial, just plug in n there, you can see, you can express it as a exponential polynomial in closed form. And well, by known techniques, this is a linear recurrence sequence over algebraic entries. And now reaching T prime means that you have a 0 of this LRS, and called that we want to know if we ever hit T prime. So we're deciding Scolum's problem. In this case, we get lucky. We can use known technology for solving Scolum's problem, in particular this solving the dimension 4 Scolum's problem. Yeah, indeed, and we solve it, or we show that you can decide it. And this technology really is using deep mathematics, like Baker's theorem for linear forms in logarithms and its p-adic variations. And yeah, this Baker's theorem really, well, it's deep stuff. So Baker got the Fields Medal for this work. Right, okay, so this was some interesting case. Another corner case, you could say, is that you can represent your system using codings of rotations. So the system is somehow modeled by the following one. You have an algebraic number of modulus 1. Your initial point is 1. And you have open arcs of the unit circle in the complex plane, right? And then you start looking at powers of lambda to the n. And you want to know whether this lambda to the n ever hits any one of the intervals. And this is almost trivial, right? This is as soon as you have an open set, you know that, well, either lambda is a root of unity and you only have finitely many points in this orbit of lambda, or the orbit of lambda is dense on the circle and you're bound to hit the set. So just to illustrate the system, it looks like this, and you want to know if you ever hit the red area. Okay, but this gives us a lot of power on what's happening in our system, right? And this allows us to go beyond mere reachability. So just for motivation, I mean, why would we want to go beyond reachability? You have these, you can think of programs where you have your structure which says something like while true, do something. Okay, so here this is modeling a thermostat system. Here we have two loops within this outer while true structure. For us, we're only going to have one while loop. But anyway, this is just to illustrate that these kinds of programs exist and you might want to know stuff about them. So here, just a toy example, you have your algorithm with 4 variables and you want to do this linear update. And you just want to know what is this program doing? You have questions coming from temporal analysis, like, do we get stuck in some set of bad states? So for example, here we define the predicates P1, P2, P3. These are from the previous example of semi-algebraic sets that are our targets. You could ask if the system satisfies the following LTL formula. So, I mean, you don't need to know what LTL is. It's just, you can think of this formula, well, it's written out there. Whenever P1 holds, then P2 must eventually fail subsequently. And eventually either P3 will hold or P1 will fail, meaning that, yeah, P1 holds whenever your point hits this semi-algebraic set defined by this predicate. And I'm saying that we can decide such properties. So to do that, I'm going to define a little more. So you have your linear dynamical system given by your initial point X and your update matrix M, and you have K many semi-algebraic target sets. And the characteristic word of this linear dynamical system with respect to these targets, well, it's the most natural one you can think of. You just define an infinite word of the power set of this alphabet 1 to the K, and your nth element, an, is the subset S of the alphabet 1 to the K, such that for each I in this set S, your point m to the nx is in the target Ti. And moreover, if you take an index that is not in this set, then your point m to the nx is not in this corresponding target. So that's a pretty natural way to define your characteristic word. And now if you're interested in temporal properties of the system, you're going to be asking questions about this characteristic word. And what we're interested in are properties given by formulas from monadic second order logic, which capture omega regular properties. So MSO, just a quick slide to get the feeling of what's going on. You have your MSO over the structure of the naturals with the inequality. And you define a finite collection of predicates that just map a natural number to true or false. And well, what does this mean? You can kind of think of it as a MSO on infinite words, and the predicates PI describes the indices where you actually have this letter I, for example. And here you have the grammar of the formulas, but just to, I mean, I'm not expecting you to remember these. As an example, what stuff you can express with this would be reachability of a target. So like reachability, as I discussed earlier, this is just the formula exists n such that pi of n holds. You can ask if you're eventually trapped inside ti. So this would be if you're interested in if you have your set of bad states, you want to know if you're eventually trapped in this set of bad states, you can ask this. And you can ask a lot of other stuff as well. So how do we define this, this problem? So you have your linear dynamical system given, so your initial point x and your update matrix m, and your k many semi-algebraic targets. So if each of these targets have intrinsic dimension at most 1, or it is contained in a subspace of dimension 3, then we can decide whether the characteristic word satisfies a given MSO formula psi. And that's the theorem. And then the hardness, again, if you think about relaxing the dimension to reachability of a target dimension 2, we can, this is again a hard problem for the Scolum problem. Okay, so how do we do this? Well, the key notion is effective almost periodicity. So an infinite word is almost periodic if either every factor appears in W only finitely many times, or it appears uniformly recurrently. So that's in other words. And effectively almost periodic word is that means that you can compute this number of occurrences of this factor if it occurs only finitely many times, or the gap between, or the longest gap between 2 occurrences of this word. And okay, so almost periodic words, if you take any ultimately uniformly recurrent word, it's going to be almost periodic by this definition. But you're allowed to have some kind of prefix that only appears once, for example. And okay, this indeed is the key notion due to a result of Semyonov. So if you have an infinite word that is effectively almost periodic, then the MSO theory over the naturals with this extending in with the unary predicates corresponding to the letters of your word remains decidable. Right. Okay. So what we need to do is we just show that our characteristic words are effectively almost periodic. As I mentioned previously, our systems were, well, either you had some sort of Scolum-like situation, or you could model them using these codings of rotations. And this was the case of just one target, but of course it's not hard to see this with several targets. Well, I mean, what the implications are for several targets. So, well, the first observation indeed was that you have either eventually constant characteristic word or a coding of a rotation. And here I've added the up to finite computable prefix. And indeed, this, I mean, it's quite a deep result. Essentially, all the Scolum-like instances will only give you finitely many times at which you hit the target, or then you're fully in this target all the time. So this gives you this eventually constant part. Or, yeah, indeed, you have this coding of rotation. So now when you have several targets, let's say they're all given by codings of rotations, you're inspecting this kind of a product of codings of rotations. And now if we want to see what this characteristic word looks like, you're first starting at point 1, and none of these systems is hitting the target. So you just have your, this is coded by white. When you take one iteration of your system, the first component you see hits the red target. The second one does not hit the blue target. And the last one does not hit the gray target. So you just have your letter red, white, white, and so forth. And you can start building this, this system like this. And well, this is exactly saying that your characteristic word is actually an interleaving of codings of rotations on the torus, on the k-dimensional torus, up to finite prefix. Okay, and what is this coding of a rotation on the torus? You have your semi-algebraic set A1 on the torus and an algebraic point. By algebraic point, I mean that each of these components is an algebraic number of modulus 1. And okay, just for the sake of completeness, I'm saying that A0 is the complement of A1 on the torus. And now you code this rotation in the natural way, that either you're in this semi-algebraic set A1 or you're not, and this is the characteristic word of that sequence. Okay, so why is this effectively almost periodic? Well, first of all, let's just have a look at the picture of what's happening. So this is a 2D torus, and I'm looking at points mapped by, well, just this dynamical system. You can see that you're building up some sort of a set on this torus. And finally, I'm adding now this target set A1. And whenever a blue point hits this blue set on the torus, I'm going to say it's the characteristic word has 1, and otherwise it has 0 at that point. And now the thing is that the closure of this orbit is semi-algebraic, and a representation can be effectively computed. This has got to do with multiplicative relations of these algebraic numbers lambda 1 to the lambda k. Okay, so then, well, as is usual in codings of rotations, you have a factor. You can encode it as a condition of an intersection of sets being non-empty. Right? So for each factor, you take B1 to Bn, you can define a open semi-algebraic set on the closure of this the orbit of this point. So with the relative topology in mind, right? Well, this is still a semi-algebraic set because A1 is, and if you just rotate it, it's still going to be a semi-algebraic set. Okay. And well, almost periodicity, this comes by compactness and well, guess and check. And this checking thing, well, this is effective by Tarski because the first order theory of the reals is decidable. Essentially, you can encode deciding whether a semi-algebraic set is non-empty, and you can compute with this stuff, and yeah, everything's good. And that's the end of this proof of why it's effectively almost periodic. And yeah, indeed, that was enough to be able to decide MSO properties of this system. Okay, so now I'm going to have this is a light ending. I'm turning to parametric reachability. So this is another kind of problem motivated by stuff coming from linear loops. So recall that this was the basic setup. You have your algorithm, you initialize your point, your variables, and you enter this loop where you do linear updates, and you want to know if you hit a point, for example. And this was decidable. But usually, I mean, not usually, but sometimes you have programs where you have input, right? There's some real numbers. Well, I mean, if you want to represent them, they will be restricted, but in any case. So now your initial point depends on the input. So it's a function of these input parameters. And you might also define your update matrix using these input variables. And even the target could be defined by these input variables. And well, we want to ask the same question or a similar question. Do we reach our target, or does this loop halt? So for a fixed input, the loop halts if and only if, when you fix the variables, well, you get an instance of this reachability problem, and well, you can decide it under some assumptions, but the halting depends on the input, right? And you could be halting on different n for different inputs. So our question, or how we model this situation, would be that we ask, does there exist input? And we allow them to be real, such that the loop halts. Okay. And to restrict the problem, we have these assumptions on how you construct your initial point, your matrix, and your target point. So again, we're working with computers, so rational functions are kind of it's a natural way to model how your input is generated. So we have our initial vector. It's a rational function on k variables in dimension d. You have your update matrix. Again, its entries are rational functions, and you have your target vector. Again, rational function entries. And we want to know whether there exists a point such that there exists an n such that m at this point to the power of n applied to x at this point a equals y. So this is the parametric orbit problem, what we call it. And well, just as an example, what's happening, we have our input S written here, and our initial vector is x of s. It's just in the 2D plane. It's the first component is 1 and the second is s. The update matrix is quite simple. we have just one, s minus 1, 1, and minus 1. Okay, so I've plotted some values of our initial vector. It's this blue line here. So now when we apply m to x and we allow s to vary, we get this curve. Similarly, m squared of s, ms squared applied to xs, we get this curve, allowing s to vary, and so forth, right? And we might want to ask, does this ever hit this red circle? Well, that's a bit of a lie, because I really want these s to equal. I mean, you're hitting the, it seems that you're intersecting this circle with this orange graph, but it's not enough that you that geometrically these two intersect. You want them to equal with the same s, right? Okay, so that's essentially the setting of the problem. And well, recalling the parametric orbit problem again, we can decide this in the case that we have a univariate system. So we only have one variable essentially, and hardness arises when you have two or more variables, and this is the Scolum hardness. So if you can solve the bivariate case, you can solve the Scolum 5. And okay, I think I still have time, so I could show or discuss a bit about this hardness. So just to go over here. Yeah, so this is the problem. We're saying that Scolum 5 reduces to the parametric orbit problem with two variables. And I'm actually saying that we can do this with constant matrix M and constant initial point X. And if you recall that we had hardness when T, our target, is a two-dimensional semi-algebraic set. Well, this is actually a situation of that sort. So this is actually giving hardness for the normal reachability without parameters if your target is 2D semi-algebraic. So here's a proof sketch. You have your, well, essentially instance of a Scolum problem. And what you do is, well, you express it using this exponential polynomial as an exponential polynomial. And we know a lot of the structure of this system. So here we can assume that lambda and gamma have the same modulus and are at least have modulus at least 1. This is known to be hard to decide. So there's no algorithm to decide such instances of the Scolum problem. Well, what we do, we just express this using real and imaginary parts. Now we're going to construct our target semi-algebraic set. So again, we're going to, well, it's pretty straightforward. We want our points in the complex, four-dimensional complex space to satisfy these two equalities. So you have A of x plus by plus cz plus dw plus e equals 0. And this is coming from this expression of the Scolum problem. So we have the same A, B, and C and D and so forth. We want this to equal 0. So that means that you have a 0 of this sequence. But we also have the fact that lambda and gamma have the same modulus. So it means that the real parts and the imaginary parts satisfy this equation. And this turns out to be a 2D semi-algebraic set. And well, reachability to that implies a deciding Scolum. For the parametric case, we can show that this 2D semi-algebraic target, you can parameterize it using two variables, and you have kind of algebraic functions. To be a bit, I'm going to be waving hands there. But then in the end, again, it's that you reach this 2D set, or this 2D two bivariate target set, if and only if you have a zero of your instance of the Scolum problem, and that gives the hardness. So yeah, I think I'll stop here. Thank you very much.